Last week, you guys performed a lab to find the constant velocity of a motorized toy cart. The problem of that lab was, what is the velocity of a motorized toy cart? We always phrase that problem in the form of a question, right? Well, today's lab is going to be an acceleration lab. So what we're going to do today is to try to find the acceleration, not the velocity per se, but the acceleration, the rate of change of velocity of a non-motorized cart that's going to be on a slant. So what do you think a good problem would be for this? Yeah, I just told you essentially what we're going to do. Phrased in the form of a question, what do you think a good problem for this would be? Perfect. Good, Luke. What is the acceleration of a cart while traveling down a slope? Something like that. Doesn't have to be exactly those words, right? But something like that. Always phrased in the form of a question, remember. What is the acceleration of a toy cart or of a cart? Don't just say that, though, because we have to specify that it's on a slope. What is the acceleration of a cart on a slope? Now, your apparatus/materials is going to look pretty much the same as last time, except this time we do require a track. Okay, we can't have a slope if we don't have a track. Notice, here's my cart. Here's my dynamics cart. Okay, this is my motion sensor. Again, exactly the same setup as you had before as far as that goes. That motion sensor is connected to the air link via a cord, and then that air link is connected via Bluetooth to your phone, your iPhone, your Android, or whatever the case may be. Also notice what's different this time, of course, is that track, and that track has to be on a slope, and there's only one way we can put that track on a slope, and that is to put something underneath one end of it. So maybe you're going to use books, maybe you're going to use, I don't know, a Kleenex box, whatever the case may be. I'll just put a little star by that because you're going to write down for your materials whatever you use, not whatever I have in my picture, but whatever you used in order to create that slope. I'll caution you, you don't want too big of a slope here. Okay? You don't want it to be too steep. You want it to be steep enough that there's actually an acceleration, that it actually starts moving on its own. But if you make it too steep, it's going to accelerate too quickly, and it's going to go off the cart before you've had a chance to collect enough data. So, you know, listen, like maybe, I don't know, maybe you do it 10 centimeters or something like that. I wouldn't say any more than 10 centimeters high for the end of that slope. All right? So what are you going to do? Well, the procedure is actually pretty straightforward and quite similar to what it was last time, except that this time you're not going to start the motor of the car and then put it down as the motion sensor is going, but rather you're going to start the motion sensor and then let the cart roll down the track. Make sense? Simple as that. Now, once you export your data, and hopefully you remember how to export your data. If you don't, then you can chat with me and I can help you out with that. Once you export your data and then import it into a Google Sheet, you're going to see 4 columns, or actually a number of columns. The 3 columns that I want you to keep are these: time, position, and velocity. The last time, if you remember, I asked you to keep only the first 2 columns, time and position, and I asked you to delete the last bunch of columns, okay? This time, I want you to keep 3 columns, time, position, and velocity. Now, once you have those 3 columns, you're going to end up plotting a couple of graphs, 2 graphs this time, both on Google Sheets. The first one is going to be position versus time. Make sure you label it properly with your axes, your units, your title. And that position versus time graph should look something like this. Then you're going to take the first column and the last column, plot a graph that looks like this. Velocity versus time. And that one should give you more or less a straight line. That straight line on a velocity versus time graph is going to tell you that you have a uniform or a constant acceleration. It's not a constant velocity, it's speeding up, but the rate at which it speeds up is staying the same. Does that make sense? And that's indicated again by the straight line. And you can tell that that first line, you guys know what that means, right? It's an acceleration, right? Because it's curving upwards. You got 2 analysis questions here that you can feel free to take a photo of right now, or to write down right now, or to just refer back to this slideshow that's on Google Classroom already. Describe the motion of the object using the position time graph, referencing the shape of the graph. So in other words, tell me what's going on in this situation. What's the cart doing? And with reference to the first position time graph, how do you know that? right? How does the shape of the first graph tell you what's happening to this card? And then the second question says, display the equation of your velocity time graph. You guys remember that you did that last time for your position time graph, right? Up here in the corner, y is equal to 0.245x plus 0.003 or whatever, okay? Display that equation and then identify which of the numbers on that equation represents the acceleration of the object, okay? I'm going to leave you with that. I'm not going to give you the answer to that. Okay? Think through that. If you really are struggling, then you come talk to me and I'll help you, not give it to you, but I'll help you individually with that, right? Then all you got to do is a conclusion. Okay, your conclusion is going to relate back to your problem. Remember what the problem was? Luke, what was the problem? Okay, so what is the velocity, the acceleration of a toy cart going down a slope? Your conclusion will be the velocity of a toy cart going down a slope is blank, and then how do you know? So what is the acceleration? And then how do you know? And that's a pretty straightforward, quick answer. How do you know? Finally, of course, sources of error. We need 2 or 3 good sources of error, not human error. Okay, we don't want to say that we made a calculation error because that's not a good one. Okay, that's a human error. We want something that could have been better with our apparatus, could have been something better with our procedure, something that could have been better with our time management, something like that. Okay, not a human error. I will remind you that if you're doing the lab and in the middle of it, you're like, oh, it would be better if I did this. It would be much better if I did this. Sometimes people have this tendency to leave it and not fix it because they figure, I want a source of error, right? I don't want to give away my source of error when I go to do my write-up. I want to still have this. Listen, if you fix something, if you do something that's outside of what I've told you that makes it better, then please do that. You can still address that in source of error. It will still count. So just because you're smart enough to do something about the problem as you're in the middle of your lab doesn't take away from you being able to use that as a source of error. Does that make sense? So if you catch the mistake ahead of time, fix it. That would be wonderful. And then just tell me, this was the error, this is how I fixed it. As opposed to after the fact, this was the error, this is how I'll fix it next time. Okay? Because of course that's what we got to do, right? Identify your 2 or 3 good sources of error, and then either identify how you fixed it or identify how you'd fix it for next time.